Hi, this is Ayan Chakrabarti, and this is a brief talk about a couple of interesting directions in which modern machine learning methods can be helped, can benefit from incorporating knowledge about the physics of measurement. So let's begin by considering the standard computer vision setting where there's something you want to estimate, depth, motion, appearance, or just say an ideal undegraded image of the scene. And what you have is some kind of image or visual measurement which tells you something, but not everything, about what you're trying to estimate. The task then is to build an estimation algorithm that goes from this observation as input to your desired output. So that's a common computer vision setting, and increasingly these estimators are neural networks. And we know when trained well, these networks can do a fantastic job at a variety of applications. But let's begin by asking, how does a network or an estimator solve this problem, or essentially what are the fundamental sources of information it has? So first of all, it has the observation itself, and the observation is informative towards the scene, even if imperfectly, and the nature of this information is given by the physical measurement model, which relates your observation to the scene. This model is typically non-invertible, which is what I meant when I said it's an imperfect or incomplete source of information. Now, if you were to go ahead and train a network on a bunch of input-output pairs, your network will implicitly learn to exploit this relationship or this measurement model, and while doing so, it'll combine it with some sort of an image or scene prior to solve the problem because the measurement model by itself is non-invertible. Now, you might ask, if your network is automatically learning to do these things implicitly, why would you want to care about physics or measurement models? So one clear reason is that knowing the physical measurement model might help you design or choose the right architecture. For example, if you're doing something like stereo, you might want to choose an architecture that is exploiting epipolar geometry in one way. So that's a clear case where you might want to use the knowledge of the physical measurement model. But in this talk, we actually won't talk about that. We'll talk about a couple of different ways in which measurement models can be useful. So the first is the setting when you have the opportunity to modify your sensor or your camera, and therefore to modify the measurement process. And what you want to do is that, given some sort of budget or constraint on your camera, you want to make the kinds of measurements that are most informative or that are complementary to your prior. And we're going to talk about how you can cast this as a learning problem as well, but what you're doing is that you're effectively learning the sensor. The other direction that we're going to talk about is in unsupervised learning, when during training you don't actually have access to ground truth, you only have access to measurements. And what we're going to talk about is how then you can use the measurement model as a means of deriving supervision in order to train your network. So let's first look at learning sensor designs. This is our pipeline again. Camera makes a measurement of the scene, which goes as input to our estimator, which let's say is a neural network. Now, instead of just learning the network as you usually would do, we also want to learn the sensor in a way that both are jointly optimal for this task. Now, what do I mean by learning a sensor? Let's take a simple example application, color imaging. And so if you have a color camera, what it's actually doing is that it's making subsample measurements of color. It's measuring only a single color at each pixel. And the estimation task is to interpolate or demosaic these measurements to get a full color image with 3 color values at each pixel. Now you can treat this as an inference problem where the camera design is fixed and it makes these measurements according to some given pattern, let's say sort of the popular alternating Bayer pattern. But you might also ask, is there a different pattern that I could use so that if I made measurements using that pattern, the overall output, it would make the interpolation task easier and give me better overall results. And what we want to do is that instead of trying to come up with this design by hand or using expert intuition, we want to learn this design from data. Just as we've been learning the inference network's weights, we also want to sort of have a data-driven way of coming up with this design. And the way to do that is to basically have a sensor layer and use the sensor layer during training, which simulates the camera and whose learnable parameters are what determine our sensor designs. And we want to learn these sensor parameters by backpropagation from the laws defined on the quality of the final inference network's output. Now the key challenge here is, of course, how do we build the sensor layer? And what we need to do is to, of course, first make sure that the forward pass of the sensor layer accurately models the physical measurement process, but we also need to make sure that this layer is differentiable and it's parameterized in a way so that the design that you get after training is something that you can actually fabricate. Now back in 2016, we actually considered this problem, and we specifically considered the problem of color imaging, and we came up with a solution where we had a sensor layer where you had one of C predefined colors that you could measure at each pixel, and we sort of learned this hard design decision by a real valued relaxation to a temperature based softmax. And it turned out to work quite well. It gave us images with higher PSNRs across a wide range of noise levels with fewer spatial or color artifacts. And since then, there's actually been a bunch of more work on sort of applying this principle to learning different kinds of sensor designs, from coded aperture to coded exposure to learning phase masks and so on. Next, let's talk about how we can exploit measurement models for unsupervised training. So let's go back to our setting, but in this case, let's assume that the sensor design is fixed and we just want to train the inference network to go from measurements to our estimate. Now, how do we train this network? With input-output pairs, or essentially pairs of observations and ground truth. And the reason we need the ground truth is to be able to compute our loss with respect to the estimate, and then to be able to backpropagate the loss to train the parameters of our inference network. Now, a problem in many applications is that ground truth is hard to get. In fact, that's quite often why we're using computer vision and building these estimators in the first place. So here's an alternative. What if instead of pairs of measurements and ground truth, we were able to use pairs of measurements to train? What I mean is that for each scene, we collected 2 measurements with some variation in parameters. So say if the problem was deblurring, we had 2 measurements of the same sharp image with 2 blur kernels. And what if we could use these pairs of measurements for training without having access to the ground truth, or without needing access to the ground truth, which is hard to get? So that's the problem we looked at in a NeurIPS paper last year. So you have this data set where for each scene you have a pair of measurements, and that's each sample is a pair of measurements. During training, you send each of them through your network, which by the way still only takes a single measurement as input at test time. And so then you get 2 estimates, one from each observation. The problem is that now you can't compute a loss with respect to the ground truth because you don't have the ground truth. So instead what we do is that we define a swap loss. So let's say to begin with, you know what the measurement parameters are, in this case what the blur kernels are for your training set. Then if you have the measurement model, you can use it to take the estimate from say the second observation and simulate measurement with the parameter of the first observation. And then what you can do is that you can define a loss on this simulated observation between the simulated observation and the actual first observation. And once you define this loss, you can actually backpropagate this loss through your measurement model, which we assume is differentiable, back to train your network. And you can do this the other way around as well. And in the paper, what we do is that we show that if your measurement parameters are random and independent and diverse enough according to some sense of being full rank, this approach will provide full supervision to your network, even though your observation model is non-invertible for a single measurement. We also have an approach for blind training, when you don't know the ground truth and you don't even know the measurement parameters for the images in your training set. Again, this ends up working quite well. We get results with unsupervised training that are almost as good as those that you get with if you had actually trained with supervision from ground truth. I'll mention a couple of other works with a similar flavor. So noise to noise is a paper that sort of came before this, which also trains in pairs of measurements for the case when your observation model is just noise. Ambient GAN is another interesting paper that doesn't actually train an estimator, but trains a GAN, but again from pairs of from not pairs, but from like a training set of just measurements. And then there's the work of Ma et al., which is also very interesting, which has which trains again with paired observations, but for the problem of intrinsic image decomposition. All right, so in this talk, I told you about these sort of 2 interesting ways you can incorporate a physical measurement model with your learning-based method. You can think of them as sort of before the input as a way of learning sensor designs, and after the output as a way of computing losses for unsupervised training. So that's all I have for this talk. Thank you so much for listening.